Welcome to the Deep Dive. Today we're unpacking a really significant technical report on a new foundation language model series, Ling 2.0. This is all about how you build a model that doesn't just, repeat information, but actually thinks and does it efficiently. We've got the sources here detailing how they scaled this thing up to 1 trillion parameters, that's the Ling 1T model, and the whole project was driven by this one idea. Every activation boosts reasoning capability. So our mission is to break down how they scaled reasoning without the costs just spiraling out of control.
And that central claim, the one that really holds it all together, is pretty remarkable. They're talking about Ling 2.0 models achieving up to 7 times the active compute efficiency compared to standard dense models. A jump like that. Well, it doesn't happen with just one tweak. It's about coordinated innovation. We'll be digging into 4 key areas where the Ling team really pushed things forward. We're talking model architecture, pre-training, post-training, and of course the infrastructure needed to handle it all. We need to see how all those pieces fit together to get that efficiency while still improving reasoning at, the trillion parameter scale.
Okay, let's start right there, at the foundation. How did they even get to that 7x efficiency number to begin with? I mean, it seems to come back to the architecture. Specifically, a high-sparsity mixture of experts, or MoE, design that they used across the entire series.
That consistency is so important. Your typical large models are dense, meaning every single parameter is fired up for every calculation. MoE just changes the whole game and introduces thousands of these specialized subnetworks or experts. And for any given piece of text, it only activates a tiny fraction of them.
And that specific setup is what gives them that hard number, that 7x figure. Could you walk us through what that design looks like for Ling 1T?
Sure. So for all the models, they use 256 of these routed experts. Now, for any token coming in, only 8 of those experts get activated, plus 1 shared expert that's always on. So when you do the math, out of 1 trillion possible parameters, only a very small sliver is being used at any one moment. The overall activation ratio is incredibly lean. It's about 3.5%. You're basically getting the power of a giant model for the running cost of a much, much smaller one.
That concept alone seems like a massive win. But I know that scaling sparse models can be tricky. They can get unstable or unpredictable. So how did they make sure that lean 3.5% activation actually delivered stable, optimal performance when they blew it up to 1 trillion parameters?
Right, and that's where the Ling scaling laws come in. And these aren't just theory. They were built from the results of over 1,000 different experiments. These laws help them choose all the fundamental hyperparameters, which is just critical for these high-sparsity MoE models. This framework, it acts as a kind of wind tunnel. They could get a high-fidelity preview of how the massive Ling 1T would perform, but at a tiny cost. I'm talking validation expenses under 1% of what a full training run would cost. That let them really push the boundaries of sparsity with confidence.
And it sounds like the scaling laws also gave them a pretty major insight that sort of flips how people used to think about scaling these huge models.
It did. And this is where it gets really fascinating for anyone building these things. The analysis showed that for a given amount of compute, the best MoE model isn't the one with the most parameters you can cram in. It's one that actually has fewer parameters, but is trained on significantly more data than its dense equivalent.
So the lesson isn't just make the model sparse. It's that the efficiency you gain from MoE should be reinvested into feeding it more high-quality data. That's what really drives the reasoning.
That's it. They confirmed that for a reasoning model, the quantity and critically the quality of the data is what matters most. And having those scaling laws to validate the approach is what gave them the confidence to claim and then actually hit that 7 times efficiency target for this architecture.
All right, that sets the architectural stage perfectly. So let's move from the structure to the substance, which is pre-training. You can have the world's most efficient architecture, but if the data doesn't teach it how to reason, what's the point? How do they build that knowledge base?
They took a reasoning-first approach to their data mix from day one. They made sure to heavily prioritize specialized data sets, specifically ones called Ling Math and Ling Code. And this wasn't a small adjustment. That focus alone gave them a 5 to 8% average bump on their key reasoning benchmarks.
A 5 to 8% gain just from the data mix is huge. But it wasn't a static mix, was it? They used a more dynamic strategy.
Yes, a progressive one. Across the entire 20 trillion token pre-training, they gradually increased the percentage of that reasoning data. It ramped up from around 32% at the start to 46% by the end. It's like you're slowly biasing the model towards analytical thinking as it grows up, making reasoning a core part of its DNA, not something bolted on later.
I think people often overlook that middle phase of training. The report mentions they introduced two really critical steps during mid-training to sort of pre-activate certain skills.
The first one was what they call reasoning pre-activation. They started feeding it chain of thought or court data during that middle phase. The goal wasn't to fine-tune it yet, but to show the model how to structure its thinking, how to lay out the steps of a problem. This sets a much higher ceiling for performance later on.
And at the same time, they massively increased its memory with the yarn method.
That's right. They took the context window from a pretty standard 4K tokens all the way up to 128K. And to give you a sense of scale, 4K is maybe a long article, 128K, that's like a short book. The model can hold entire complex code bases in its working memory. By doing that mid-training, the model arrives at the final stages already knowing how to handle and reason over huge chunks of information.
Even the training scheduler they used was innovative. The WSM scheduler warm-up stable merge.
The WSM scheduler gets around a common headache in training these giant models, which is the learning rate decay. Normally, you start learning fast and then slow it down over time. WSM just gets rid of that decay schedule and replaces it with checkpoint merging.
Can you break that down? What does checkpoint merging actually do for the model?
Think of it this way. Instead of a sudden drop in the learning rate, which can sometimes jolt the training, WSM just periodically averages several of the model's recent states, its checkpoints. This averaging naturally smooths things out. It's a bit like annealing, cooling metal slowly to make it stronger. This process makes the training more stable without those abrupt changes. And the data shows it worked, giving them a consistent 1 to 2% gain across their benchmarks, a benefit that stuck around right through to the end.
So WSM ensures the model going into the next phase is as robust as possible. That brings us to that final refinement stage, post-training. How do they take this efficient, pre-activated model and really sharpen it into an adaptive reasoning machine?
They began with something called decoupled fine-tuning, or DFT. This is basically about teaching the model to have two distinct modes, depending on what the user needs. And they did it using different system prompts. So system prompt 1 is for your everyday tasks, instant response, fast and to the point. But system prompt 2 pushes the model into a dedicated in-depth reasoning mode. This decoupling means when you ask it something complex, it doesn't just give you the quickest, most superficial answer. It's trained to use that deep reasoning pathway we've been talking about.
Okay, so that makes sure the capability is there.
Yeah.
But how did they teach it to be adaptive, to know how much reasoning a problem actually needs?
That was the job of their reinforcement learning approach, which they call evolutionary chain of thought, or Evo-CoT. Evo-CoT is all about instilling that adaptive reasoning. It teaches the model to scale its thinking. Simple problem. It gets rewarded for a quick answer. A really complex problem. It gets rewarded for generating a much longer, more detailed chain of thought. And the reward function they used was composite. So it's not just about getting the answer right. It's also about, controlling the length and format, really pushing it towards efficient but high-quality reasoning.
And the actual algorithm they use for this, linguistic unit policy optimization, or LPO, that's new as well. Why not just use a standard RL algorithm?
LPO is such a key detail here. Most RL in language models works at the level of individual tokens or whole sequences. LPO is different. It treats whole sentences as the basic unit for updates.
Why sentences? What's the advantage of operating at that level?
Well, if you're trying to teach a model a reasoning path, a chain of thought, a sentence is a much more natural unit of meaning. It represents a single step or a complete idea. By optimizing at the sentence level, LPO just gets a much cleaner, less noisy signal from the reward. This leads to more stable training, and they saw about a 10% improvement on complex reasoning tasks compared to token-level methods.
It's a really cohesive approach, aligning the optimization with the very thing they're trying to teach. And the report shows that this whole multi-stage process paid off. The evaluations confirmed that starting with CoP data in pre-training led to a higher performance ceiling after the decoupled fine-tuning.
That's the proof in the pudding right there. It shows every stage successfully built on the last. The architecture provided the efficiency, the pre-training data taught it the fundamentals of thinking, and then the fine-tuning taught it how to think adaptively and efficiently.
Of course, none of this innovation matters if the computers can't actually handle it. Scaling to 1 trillion parameters is a monumental engineering challenge. What were the biggest breakthroughs on the infrastructure side for Ling 1T?
You really can't overstate the stability challenge at that scale. A huge achievement was their implementation of full-scale FP8 training. Ling 2.0 is the largest open-source model that has been trained entirely in FP8 precision from start to finish.
Moving to FP8 to 8-bit floating point. I know that saves a ton of memory and adds speed, but it's famously unstable. Why take that risk?
The payoff is just too big to ignore. FP8 cut their memory usage by over 15% and gave them a serious speed up. They got around the stability risk by using very, very fine-grained quantization methods, and it worked. They maintained stability over 900 billion tokens of training. The accuracy hit was tiny. The relative loss difference was kept within 0.25% of the standard BF16 baseline. You need that kind of gain to hit the 7x target.
And beyond precision, just moving all that data through a trillion-parameter MOVI model must create incredible bottlenecks.
Especially since you mentioned the architecture isn't totally uniform, it has specialized layers.
Exactly. It creates a huge pipeline problem. Because different parts of the model have different compute needs, a simple schedule leads to these gaps, these pipeline bubbles, where expensive hardware is just sitting there, idle. To solve that, they built a system called heterogeneous fine-grained pipeline parallelism. They used a technique called interleaved 1F1B scheduling with some partial recomputation. If you think of the data pipeline like an assembly line, they're essentially running two lines in perfect sync to make sure there are no empty spots, even with those non-uniform parts.
And that coordination directly translated to more speed.
A lot more speed. This approach cut down on those pipeline bubbles dramatically, which is incredibly hard to do in a sparse MOE model, and it boosted their overall throughput by about 40%. It just really brings home the point that this wasn't just about clever algorithms. It was about designing the algorithms and the architecture to work with the infrastructure from the ground up.
That co-design approach was actually formalized in their software engineering guidelines under what they call the 4C principle. Correct. Consistent, complete, and co-design. It's a philosophy that ensured, even at the trillion-parameter scale, the software and hardware were never developed in isolation. So if you put it all together, the Ling 2.0 series is this fantastic demonstration that you can scale reasoning capability efficiently. You do it through this tight alignment of extreme sparse activation, that 3.5% number, with very smart reasoning-focused data and algorithms all running on hyper-efficient infrastructure. Ling 1T really does set a new benchmark for the trade-off between reasoning skill and the computational cost to get it.
So as you think about all this, here's a final thought for you to explore, and it comes directly from the Ling team's own report. While Ling 2.0 is a huge leap, they note that the current attention architecture they use, grouped query attention, actually becomes a bottleneck in very, very long context situations. The team is already signaling a move towards linear and sparse attention designs for the future. So the question to consider is, how will that next architectural shift, moving away from the technology that powers so many current models, change the game for stability, efficiency, and the ultimate reasoning power of the next generation of truly thinking machines?